Hi everyone and welcome to video number 6, the last but not least, and this one is all about neutron decay, and this is the 5th possible option that an atom could use in order to decay to become nice and stable again. So this one is quite easy because it's exactly what it says on the tin. Neutron decay, a neutron is emitted. So let's have a look. For this example, I've chosen an element, the element boron. So an atom of boron has a mass number of 11. That tells us that there are 11 particles in its nucleus. It also has a Z, an atomic number or a proton number of 5, which tells us of those 11 particles, 5 are positive protons. So let's have a look in the picture. So at the moment we have our unstable, write that in, nucleus. So we have an unstable nucleus and we'll just count up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 subatomic particles in this nucleus. 11 subatomic particles in the nucleus, as we can see here. And it's unstable. Remember, that means the strong nuclear force holding this together isn't quite strong enough, so things have become a bit rocky, they're a bit unstable. In order to become nice and stable, as we can see over here, you might be able to spot the difference in that this neutron here has been emitted. So we can see that in order to become stable, a neutron has been emitted, and we can see that from the green arrow. So we've taken this neutron here and we've emitted it, we've kicked it out. This is just a neutron, no transformations, no waves, just a neutron gets booted out. So we have our neutron has been emitted. So let's check what we're left with. So we go over to where it's nice and stable, put the smiley face in because our atoms prefer to be stable. And let's count up what we've got. So we've got a nucleus with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 subatomic particles. So this atom now, this nucleus, has a mass number of 10. So we can write that in. Its A is now 10. And let's check the number of protons. 1, 2, 3, 4, 5. So of those 10 particles in the nucleus, 5 of them are positively charged protons, and we've just counted those up. So that's quite convenient because 5 protons is what we started with. Look, we started with 5 protons. So we know because the Z, the atomic number, has not changed, the identity of the atom does not change. It's still a boron. Although it's a slightly more stable boron atom, it is still a B, it's still a boron. So we can put that into equations. We started out with the unstable version. Make sure we put that on. Unstable boron with 11 particles in the nucleus, 5 of them being protons. And a neutron is emitted. And that's nice and easy to write too, because neutrons have a mass of 1, relative mass of 1, but they don't have any charge. They're neutral, no charge. So 0 down at the bottom. And we know that we were left behind with something that had 10 subatomic particles in the nucleus, and 5 of them were protons. 1, 2, 3, 4, 5. And because that 5 has not changed from here, because it's the same number, it's still the same identity. So it's still a boron, just a more stable isotope of boron. So we can fill that in as B. Finally, looking at the general terms equation, as always, we've got our atom X, which is the unstable version that needs to decay to become stable, with its mass number of A and atomic number of Z. And it kicks out, it emits just 1 neutron, nice and simple. So 1 neutron has been emitted, just like here, and that leaves behind an atom that has the mass number has actually gone down by 1 because we started off with 11 things in the nucleus, we've now got 10 because that neutron has been emitted. So the A is actually -1 in this example. We've gone from 11 down to 10. However, the Z, the number of protons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, the Z does not change because it's a neutron that's removed, not a proton. So we can leave the identity of this atom as X. It's just a lighter isotope, a lighter version of our starting one. And that's nice and stable. So that completes our look at all of the different ways that an unstable nucleus can decay to become stable, with neutron decay being, I think, the simplest and the last. Okay, I hope all that was helpful.